Hello, myself Dr. Anirudh. I am going to present you fourth experiment of your analog electronics lab, and this experiment is determination of amplification factor of JFET. JFET is junction field effect transistor. It is a voltage control device. There is a number of transistor, MESFET, JFET, BJT, and BJT and UJT. There is a many type of transistor. This is among them. In this transistor, what we have, this is a silicon. This is a silicon or other semiconductor, that is gallium nitride, ZNO or something. If I make two PN junction, one is this side and there is this side. If I make this PN junction, two PN junction, this side and other side, and we make them reverse bias or forward bias, and corresponding to this we can control the current in this. This is also called as VVR. This is voltage variable resistance. Means you can vary the voltage and you can change the resistance. So this is also called as voltage variable resistance device. This is also called as voltage variable resistance device. Is a family of your field effect transistor. It is a family of field effect transistor, not VGT. It is a family of field effect transistor, JFET. The input means BJT is your field effect transistor is better than BJT in case your field effect transistor is your field effect transistor is voltage control device and input impedance of this is very large in comparison to BJT. So this is a advantage of your field field effect transistor in compared to BJT. So the aim of this experiment is to obtain the drain and transfer characteristic of field effect transistor and drain resistance. By using drain characteristic and transfer characteristic, you can calculate the on resistance, that is the resistance of your channel. That can be vary, as I told you just now, that can be vary by voltage. When you change the VGS, you can change the RD value. So this is a voltage controlled resistance, and then you can find the GM, transconductance, a relation of output current to input voltage. Input voltage is VGS and output voltage is ID. So you can find the relation between output current to input current, output current to input current. So that is transconductance. And if you take the product of, I will explain how this is coming into voltage gain, that is delta VDS divided by delta VGS amplification factor. So this is the requirement of your circuit. You means to do this experiment, you require a field effect transistor, that is VFW10. Another component which is required for this experiment is digital multimeter. Then you require a PN junction, that is 1N4001 type, and then you need a regulated power supply that will change its voltage from 0 to 30 volt. Then you need a breadboard, and finally you need a resistance 220 ohm that you can use for load also sometime. If you are going to design a mic, it has 20 ohm resistance or something, some rating of power, but here you can consider this resistance as a biasing voltage, a biasing parameter, or you can treat it as a load resistance, whatever you as your wish. This is the circuit diagram of your field effect transistor, that is JFET, not field effect transistor, that is the JFET, junction field effect transistor, junction field effect transistor. So junction field effect transistor, here you are connecting a voltage, here you are connecting a diode which is connected in forward bias, because a negative polarity of this variation, also this variation indicating the varying in the voltage, 0, -0, -2, -3, like that. Don't consider this as a changing in polarity. This is not changing in polarity. Polarity is always connected here until you are not connecting this here positive and negative this side. So this diode, if you don't use this diode, no problem. you can remove this diode also. Means here if you are connecting the diode in forward bias, here you will get 0.7 volt drop, and that 7 volt 0.7 volt drop will help you in calculating means biasing for this JFET, junction field effect transistor. So simple is means a little bit straight here, but means that is some tilted, means tilted you can get. This is the junction field effect transistor. Here you have a channel, here you have a channel, and here you have a drain and source, and this arrow indicate a PN junction here. This arrow indicate a PN junction here. You are having a PN junction here. So this is the drain and this is the source, and you have a PN junction here. And this side, when you are considering this side of the circuit, it will provide you, this side of the circuit will provide you, this side of circuit will provide you means output characteristic or static characteristic in this experiment. Static characteristic means in this experiment. And if you consider VGS and ID by fixing VDS, then you get the transfer characteristic. How you will do that, I am going to explain you. And this is your supply voltage. This voltage again vary from 0 to 30 voltage. You need this voltage to vary this VDS and ID. You apply this voltage to vary this VDS and I. You apply this voltage to vary VDS and I to measure the ID-VD curve at a fix of VGS. Similarly, this voltage can be used to fix the VDS to measure the VGS and ID, to measure the transfer characteristic, So here first of all you have to measure the static characteristic. In static characteristic you have to connect the circuit as shown in the figure. First you have to connect the circuit as shown in this figure. Once you fix the figure, then connect the circuit like as shown in the figure, then keep VDD is equal to 0. What? Keep VDD is equal to 0. This VDD is equal to 0. If you make this 0, this VDS is also going to 0. And then VGG is equal to VGG. Set this VGG in a such a way, so that VGS read 0 voltage. First condition, VGS is equal to 0 volt. Now then what you have to do, in VDS you will vary VDS from 0 to 10 volt. Here 0.2 volt step size for 0 to 1 voltage, but I recommend you can vary 0 to 10 volt and in the step of 0.2 without loss of any accuracy. But if you do this instead of here, if you do that, then your result could be better. In that case your result will be better. So here once you increase VDS from 0.2 means 0 to 10 volt, measure the ID. What? Measure the ID and note down this in this figure. VGS is equal to 0, you fit. Then VDS is equal to 0 to 10 volt. Corresponding you measure the ID. Now what you do next? Means in next again fix the VDD is equal to 0 volt. Now increase the VGG so that VGS become minus, means VGG increase in such a way your VGS become minus 1 volt. Increase only, but in negative direction, minus 1 volt. When you fix VGS is equal to minus 1 volt, then come at this side VDS. Now VDS again change from 0 volt to 10 volt. VDS change again from 0 volt to 10 volt and note down the ID. Then again set VDD is equal to 0 volt and VGS is equal to now set minus 2 volt. VGS is equal to set minus 2 volt and you increase your VDD in such a way your VDS vary from 0 to 10 volt and note down again ID. So one more thing I want to tell you, I would like to request you कि make means VDD is equal to 0 volt and again make VGS is equal to plus 2 volt or 1 volt, positive value also you have to take. This is normally on device, that's why you are keeping VGS is equal to minus 1 volt, minus 2 volt to decrease the value of ID current. But if you want to increase from beyond the 0 volt, means VGS is equal to 0, if you want your transistor current increase with that, increase from that, then what you will do, you will increase the VGS in positive direction. You increase the VDS from positive direction, increase the VDS in positive direction. So increase the VDS in positive direction. So this is the way. Now come to the transfer characteristic. In transfer characteristic, as I told you, you will make VGG first 0, and this is a graph between ID and VGS. It is a graph between ID and VGS. This is a graph between ID and VGS. This is the graph between ID and VGS. This is the graph between ID and VGS. If you do that, then means how you means if you do that, you will get the transfer characteristic and transconductance. So in what in this you have to fix VG is equal to 0, then VGS you will get some VGS value, and now VDD, said we increase VDD in such a way your VDS become 5 volt. I recommend first measure in 0 volt. Then vary VGG so that your VGS change from 0 volt to 5 volt or like that. In the step of 0.5, you can take the step of 0.2, you can take the step of 0.25 or like that, and then again make VGG is equal to 0 and set your VGS VDS 10 volt, 5 volt, then 10 volt. Again repeat, increase the VGS, measure the ID, In this way you will get this plot. VGS ID at different VDS, VGS ID at different VDS. VDS is equal to 2 volt, 0 volt as I suggested you. VDS is equal to 5 volt I suggested you. Then means you will get complete curve like this by using repeating this two. If you plot this, VGS and ID, you will get this curve at some VDS. If you plot this side VDS and ID, you will get this curve. So from here you can calculate the RD on resistance, which is defined by this equation. RD is equal to delta VDS and ID. This is inverse of S. S is the slope. First find the slope here. First find the slope of this curve in the active region. Just find the slope of this. Then you can calculate RD on resistance. That is the ratio of change in voltage, drain voltage to change in drain current. RD is equal to delta VDS upon delta IDS. VGS is constant here. VGS is constant here. Here VGS is equal to constant. You can see from here VGS is constant. When 0 voltage, then you will get 1 RD. If VGS is equal to minus 1 voltage, then you will get another RD. If VGS is equal to minus 2 volt, you will get another RD. This RD depends on your 0 voltage. Because of this reason only I told you this is the voltage controlled resistance, VBR. This is the voltage controlled resistance. Now come on transconductance. Transconductance is the ratio of change in drain current to change in VGS. So from where you will get, if you concentrate on this, you will get that the slope of this curve is giving you your transconductance. The slope of this curve giving you your transconductance. From where this curve is coming? By plotting this VGS and ID. ID versus VGS at a particular VDS. You can here one curve I shown to you, but you can get a family of curve by changing the VDS, by changing the VDS. So you can get the family of curve, and you can get transconductance, that is that will vary with the VDS voltage. Okay, because this is when you change this slope will change, and this means this curve will change, and that slope will change also. And if you take the product of this, if you take the product of this RD and GM, then what you will get, just multiply these two, RD and GM. If you multiply this, then what you will get, delta VDS upon delta VGS, because delta ID will cancel with each other, then you will get delta VDS upon delta VGS. So RD GM is equal to your voltage gain. GM into RD is your voltage gain. I hope this will help you in conduction of your experiment. Thank you for your attention. Have a nice day.